right? So today we will define and begin to use non-deterministic push-down automata, which are the equivalent for context-free languages of the final automaton, uh, deterministic or non-deterministic, that we saw. So we will prove in the next class that um, non-deterministic push-down automata can asset exactly the languages that can be generated by context-free grammars. In other words, both NPDA and CFGs talk about the same class of languages, the context-free languages. So let's look at the language we have seen many times now, A to the n, B to the n, where n is a natural number. And we showed, using the pumping lemma, for example, that A to the n, B to the n cannot be asserted by a finite automaton. So why is that? What is the key limitation of finite automata that prevents them from being able to assert such a language? And the idea, the reason is that to recognize this language, the finite automaton would have to count the number of A's up to an arbitrary large n, and then count down from n to match the number of B's. And the problem is this arbitrary large conflicts with the idea that finite automata have a finite amount of memory. So FAs in general cannot accept this. But why can context-free grammars not accept, because they don't accept, they generate, but why can the context-free grammar generate this language? Because in a sense, when they generate this language, context-free grammar also needs to count, right? It needs to be sure that the number of A's it generates is the same as the number of B's it generates. Or maybe if it generates the A's first, it can generate an arbitrary number of A's, but then it must remember how many it generated to generate the same number of B's. So in other words, context-free grammar somehow remember n. That's the key piece of information. So for example, if you consider a Gray-Bach normal form grammar, S goes to A, S, B, or epsilon, and then B goes to little b. In a sense, the variable B's that are generated are a unary counter of the number of A's that are being generated, because every time, so S generates A, S, B, then it generates A, S, B, B. And let's say let's do it one more time. So we have this. With the Gray-Bach normal form, it's very easy to see how this counting works. The grammar so far has generated 3 little A's, and it remembers that it will have to generate 3 little B's, right? And so then simply says, okay, I'm done generating A's, let's begin to generate the B's, and so S goes to epsilon, and then simply each of these becomes a B one at a time, right? So A, little b, big B, big B, and so on, right? So the idea is that the context-free grammar can remember the A's, how many A's generated by keeping variables around, right? And of course, because the context-free grammar, the number of B's can be arbitrarily large, right? Because it's a counter essentially, right? It's not bounded like for a finite automaton. So this suggests that if we want to define some type of automaton that can accept this language, we need to equip the automaton with some kind of counter or memory, and that memory must be arbitrarily large, right? It must not be bounded, because if it were bounded, if I can count up to 1,000,000, then I can do it with a finite automaton, right? 1,000,000 is a lot, so I need a lot of states, but it's a finite number. So now we define a NPDA, non-deterministic, because we'll see it's non-deterministic, just like an NFA. Push down, because it uses a stack as the arbitrary large memory. And a stack you push down, and then you push and you pop. And then automaton, because it is an automaton, all right? So an NPDA, we write it again, M as a machine. So we're going to write it similarly to an NFA, but it has a few more components, because we need to also discuss what the stack does. So Q, sigma, uppercase gamma, that's a Greek letter, delta, Q0, little z, f. Okay, so we have the delta and the QZ, the z are going to be different. There, now I have two hands free. Okay, so this is new, and the delta also will be different, okay? All right, so Q is a final set of states. So that's exactly the same as for an NFA. So that's the final control of the machine, right? So we'll see all the machines in this course have a finite number of states. Sigma is the input alphabet. And gamma is the stack alphabet, because everybody, well, if you are a computer science major, you know what a stack is. Otherwise, you're going to see it, but essentially it's exactly a stack of pieces of paper on your desk, right? So you put it on the top, and you push on the top, and you pull from the top. You cannot go and pick it from the middle, okay? All right, then the delta is, let's write it correctly here, okay? So delta is a function, it's a non-deterministic function, right? So goes from Q cross so it is in a state, it reads an input which can be a symbol, one of the alphabet, or epsilon, just like an NFA, it can make epsilon moves, and gamma. So it reads the top of the stack. So it doesn't read the entire content of the stack, but just the symbol on the top of the stack. And there must be one, because it's not sigma star, it's not sigma 0, it's sigma. And it goes into what? It goes into the moves are of this type. So it's a finite set S of things of this type. And what are these? Well, these are the new state, and gamma star is the string that gets pushed onto the stack when the symbol here, the symbol on the top of the stack gets popped. So, well, let's keep going, and then we'll see an example, or two or three. So Q0 is just the initial state. And what is little z? Is the initial stack symbol. So just like I need to know in which state I start, I need to have something on the stack at the beginning. Why? Because otherwise I cannot move. The moves are always defined, for example, on sigma 0, so on Q0, I will have some input symbol, or maybe I do an epsilon move, and I need to read something on top of the stack. So at the beginning, I need to have something on top of the stack, and so this is the initial stack symbol. And then F, as usual, is a subset of Q, is in just the final states. So let's define the delta a little, well, this is defined, but let's make it a little more understandable. So if we have that P beta 1, beta 2, beta n is in the delta of Q A alpha. So Q is going to be an element of the states, a state. A is either an input symbol or epsilon, and alpha is the symbol on the top of the stack. So if I define that this is one of the possible moves, right? So P beta 1, beta 2, beta n belongs to this, means that delta can have many moves in this situation. This is one of them. So what it means, let's draw it graphically. So if I have a stack, this is the stack, and on the top I have alpha, right? And then I have the control is Q, and on the tape, let's say A is a symbol, so I am here, right? So this is the input tape or the input string, and I've read something, and now the next symbol is A. So if this is the situation, what does the MPDA do? From Q, it goes to P. If A is the actual symbol, it will consume it, and then it will read the next one, if there is a next one. And then alpha gets popped, so it goes away, and beta 1, beta 2, beta n get pushed down, and just don't make, I mean, we can decide in which order they get pushed down, and the way I defined in my notes is that it gets pushed down this way, so it's beta n here, dot, beta 2, beta 1. So beta 1 will be at the top of the stack, okay? We could have defined the opposite, but we define it this way. Let's just agree that this is the way we are going to use it, because when you define it, it's not going to be the same if you push it this way or this way, obviously. All right. So in one move, this is what will happen. Now, if A is epsilon, that all it means is just that this position in the input string will not change, and this move will happen regardless of what's under the head, or maybe there is nothing, right? Maybe I'm at the end of the input. So we define the language accepted by the MPDA M to be equal to the W in sigma star as usual, such that there exists a state P that is final. There exists a U which is a string of gamma of stack symbol. And if I start from the initial configuration, which is Q, W, Z, so that's the initial configurator, Q0 is the initial state, W is the input string, and Z is the initial stack symbol. In some number of steps according to delta, as I just showed, I will go to the state P, which happens to be final. I will have consumed all of W, and I will have U on the stack. So this is very important. The string W is accepted if it can be consumed, right? So I need to start with W in input, and at the end I need to have epsilon on the input. So I've read the whole, so I was able to read the whole string. Of course, P must be a final state, right? Just like for an NFA. But look what happens with the stack. The stack initially has one stack symbol, the initial stack symbol, we'll call it usually Z or something like that. At the end, I can leave the stack dirty. Right? I can have anything. U is just anything. It can be epsilon, it can be Z, it can be some string of symbol that I pushed. It doesn't matter, right? Now, and again, this is non-determinism, and so as long as one of the clones, right? Because when, remember, just like an NFA, when the delta allows different moves for the same Q input and stack top, the NFA will clone. And if one of the clones can reach a situation like this, then the string is accepted. So there are essentially two ways for a string not to be accepted. One is that all the clones that manage to read the whole string, so end with epsilon, are in states which are not final. And the other is, for the other clones, they don't even manage to consume all of W, right? Just like on NFA, NFA can get stuck, right? If it doesn't have a move out of a state for the given input symbol. And in this case, it will be for a given input symbol and the given top of the stack, right? So let's do a few examples, and hopefully it will be more clear. Now, most of your exercises, or many of your exercises, you will actually be epsilon. In other words, very often, just like when you write a good program, things are nice and clean. When you write a good NPDA, likely the stack will be empty at the end, but it doesn't have to be. However, there are definitions that actually require the stack to be empty at the end for the string to be accepted. So instead of U here, I would have epsilon, and that's fine because you can prove that if this happens for some clones, then you could change the grammar, the NPDA slightly so that the clone will accept, and the stack will be nice and clean, empty, okay? But in this class, it's okay to leave the stack dirty. All right, so let's do a few examples. It will hopefully help. Well, let's start with A to the N, B to the N, right? And we already saw the idea that we want to count the A's as I generate them, as I read them in this case, because I'm accepting a string. So as I read the A's, I need to remember their number. And then I need to match this number with the B's. And NPDAs use a unary way of counting. just like 1, 2, 3, 4 are just the number of ticks on a wall, right? Okay, so let's define the MPDA for A to the n, B to the n. So I use Q0, Q1, Q2. So 3 states. Of course, sigma is A and B. And gamma, of course, it contains little z, because that's my starting symbol. And just a bar, 1, right? Just a counter. The delta will be the key part, so we'll define it separately. The initial state is Q0, the stack symbol is Z, and the final set of states is just Q2. Okay, so let's see what delta is for this to work. So the delta of Q0 epsilon Z. So if I am at the beginning in Q0, the initial state, and the stack as Z, so it's the only thing it has, I can do an epsilon move right away. And so I can go to Q2 and epsilon there means I pop the Z and I push nothing on the stack. So why do I have this move? Well, because what is the shortest string here is epsilon. So I must be able to asset epsilon. And this does that, because if I am at the initial state without reading anything, I just pop the top symbol, I go to Q2, and then that's it. Because when I'm in Q2, with epsilon on the stack, I cannot do anything, because with epsilon on the stack, there is no move defined when the stack is empty. But I am in the final state. And so I will be assetting epsilon, which is the right thing to do. However, if the input is AB, and I make this move, I will have a clone that will be in Q2, final state, with the stack empty, but there is still A and B to be read, so that clone will not asset AB. Well, we are not determinism, so there will be another clone that will asset it. So the delta of Q0 on an A with Z. So again, I have Z at the beginning, right? And I have an A in input. What do? I read the A, and I remember that I read 1A. And I do that by going to some state Q1, and I push a 1 on the stack, so I remember that I've seen 1A. And the way to write this is this. So why? Because remember, the move says pop, read the A, pop the Z, but then you want to put back on the stack a string, and the string is Z1. And if you think about it, if you pop a Z and you push back a Z and a 1, then essentially you have pushed the 1 on top of the Z. But that's the way to write it. Okay? Sorry, I'm still in Q0 actually here, right? Not in Q1, this is Q0. So now I'm still in Q0, initial state. I have 1 top of the stack, so this move will not be possible because I need to have Z on the top of the stack. But I might be reading more A's. So Q0A, if I have a 1 on top of the stack, which means I already have read some A's, what do? I keep pushing the 1. So I stay in Q0. And again, I pop a 1, and I push 2 ones, which is the same as adding 1 1 on top of the stack. Adding a single 1 on top of the stack. Well, so I can keep doing this. So let's see. If we are in Q0, we input A, Z. In one step, well, one clone will do this, for example, and then, so let's do it, and we'll just, sure, we can do this. Okay, so we'll do, we'll go to Q2. For epsilon will be A, epsilon, and then this will die, right? Because I have not read all of the input. I read none of the input, and I don't have anything on the stack, so I cannot move anymore, right? So this will be a clone that will die, but instead, this one will go to Q0. So if I make this move instead, I read 1A, so I have 2 left. And I pop the Z, and I push 1Z, so I will have 1Z. And now I can make only this move. And so I go Q0, A, 1, 1Z. Right? So again, I read an A, I pop a 1, and I push 1, 1. Let's do it one more time. Q0, I have epsilon, and I have 1, 1, 1Z. Well, obviously, what do I want to be true? I want to be able at any one point, if I've seen some number of A's, so I have a 1 on top of the stack, right? So the if I have I don't know what the stack is, right? The NPDA can only look at the top. If the top is a 1, it means I've read some number of A's. It doesn't know how many without popping the ones. But there must be at least one A that's been read, right? So I must be able to start processing the B's. So if I am in Q0 and I have a B in input and I have a 1 on top of the stack, then what do I want to do? I want to change state, so I go to Q1. Q1 will be the state in which I am now popping ones from the stack instead of pushing them and matching them with the B's. So I must read the B, and I push nothing. Right? So in other words, I pop the 1 and I put back nothing. So here, what would I do? Let's say that the string was BBB, AAA, BBB. So now I have AA, BBB, A, BBB, and instead of epsilon here I have BBB. So from Q0, BB, 111Z, I go to Q1, BB, 11Z. Right? So if the string was a correct a string of the language, so 3 A's and 3 B's, now I'm left with the 3 B's, and I have 3 1s on the stack, lucky me. So I match 1B to the 1, I have 2 left. I do it again, I go Q1, B, 1Z. I do this once more, and I do Q1, epsilon, Z. And then what do you think? I am in state Q1. I have nothing to read in input, and I Z on top of the stack. Now, of course, the NPDA doesn't know, it doesn't have anything to read, right? But the NPDA should be able to say, well, if I am in state Q1, and I have, without reading anything, I have Z on top of the stack, I want to go to state Q2 and just pop the Z. So if we do this here, we go to state Q2. We have nothing on top of the stack, so we cannot do any more moves. We have read the entire string. So by definition, AAABBB is accepted by this MPDA. Okay, so that's good. So we have shown how the MPDA would work on a string in the language. So let's say if you only had two B's or no B's, we already saw that, right? If you had no B's or fewer B's than A's, you would end for example, here, let's say if you had two B's, right? Instead of three, you would have two here, one here, no B's here. So now you have nothing in input. You have one Z. You will not be able to transition to this state because this transition is only possible, the Q1 epsilon Z to Q2 is only possible if you have Z on top of the stack. So essentially it means what? You will be stuck because you have read the whole string, but you are in a non-final state and you cannot move to the final state because you have one Z on top of the stack. So that wouldn't work. The other possibility would be, what if I have four B's, right? Well, if I had four B's, so three A's and four B's, you would have this situation, right? So now the MPDA would be in the final state, the stack will be empty, but the input string would have not been consumed, you still would have a B left, which means the string is not accepted again. Okay? I guess another possibility for the string not to be accepted would be, what if you had AAA, BB, A? Well, that's very easy. You do these steps. So the clones will do. You will be left with BBBA, actually with BBA. Okay? And so you would, in this case, actually, you would not be accepting because you have the one on the stack. And you cannot match it with a B. If you had AAA, BBBA, you would be in state final Q2, but you have one extra A which you cannot process because there are no moves from Q2. In other words, when you will start doing your exercises, the difficulty in MPDAs is the same as for NFAs, but even larger, because you need to think about all the clones, right? You need to be sure that there is no way that any of the clones will get to an accepting state if you don't want to accept. And vice versa, you want to be sure, but that's usually easier, that the MPDA, one of the clones will go to a final state if the string is in the language. But what often you need to be careful is that you don't want to accept strings you don't want to. Because with non-determinism, you have all these squishy clones that are going away from you, all right? Okay, so now writing this is a big pain in terms of, just text. So we're going to actually draw them just like we do for VFA and NFA. So here is the convention that you will use when you write, when you draw an NPDA. So it's not that different from an NFA, it's very similar in fact. Except you need to tell me what happens to the stack, because there is this additional piece of information, right? The stack. So I'm going to now draw graphically the NPDA that I just draw textually here. And from now on, Don't do them textually, do them graphically, please. Actually, it's not a please, it's a request. So I have the initial state. As usual, I need to say this is the initial state. I put an arrow there. But now I also need to say what's on the stack. So we'll write init z. And by the way, z is the default value. So use z for the starting symbol. Sometimes you might want to use something different. That's fine. There might be a reason to use something different, but otherwise just use z, because if we see z, we immediately know you're talking about the initial stack symbol. So what do I want to do when I'm in Q0? If I see an A, right, that's the only thing I want to see when I'm in Q0 is an A. At the beginning, I want to read the A's. So if I read an A, what do I do? If I have a Z, I pop the Z and I push one Z. If I have a 1, I pop the 1 and I push 1, 1. So pop Z, push 1Z, A, pop 1, push 1, 1. Right, so these two are essentially these two moves. Otherwise, if I'm in Q0 and I see the B, I change state. So B, I must be able to pop a 1. If I have 0 on the stack and I start with a B, I have an error, so I don't want, I have a signal in the language, so I don't want to do anything. But I do a pop 1. And what do I push? Nothing. So I push epsilon. I go to state Q1. In Q1, what do I want to do? I want to read the B's and match them with the 1s. So B, pop B, push epsilon. If I am in Q1 and I want to say I'm done, what do I need to do? Without reading anything, so epsilon, I want to be sure there is a Z on top. How do I do that? I say pop Z, and I push back nothing, push epsilon, and I go to the final state Q2. But I also had this initial move here in case I wanted to set epsilon, because it's in the language. And so from Q0 on epsilon, if I have Z on top, I will pop a Z and push epsilon. All right, so this is a graphical representation of this textual information, but we are going to be a little faster. Okay, so formally, this is what you should be writing, because the delta says you read the B, you pop something, one symbol, and you push a string. Well, so let me simplify your life a little bit, but keep in mind, this is what happens. We're going to agree that we can simplify, but the meaning will be this. So you don't ever need to be push epsilon. You need to write it. Right? It's understood that if you don't say push what you're pushing nothing. You're pushing epsilon. Right? So in other words, here I can just write, if you're in Q0 and you read a B, you pop a 1. Same thing here. If you're in Q1 and you read a P, you pop a B. Sorry, this should have been pop 1. Okay? You can pop input symbol, you can pop stack symbol. Okay. So the first implication is you can push epsilon without saying it. Okay? The other simplification is, look at these. I say pop Z, which means I must have a Z on top, but then I push back the Z with a 1 on top. Or else I say, if I have a 1 on top, pop the 1 and push 1 and the 1 again. In other words, if you look at this, all it's really saying is, if I have an A, I must have either a 0 or a 1 on top. Why? Well, because that's the stack alphabet. But all I will do, I will just push a 1, right? Because if I have a Z on top, I push a 1 on top of it. If I have a 1 on top, I push another 1 on top of it. So I will let you write just A push 1, which means regardless of what the stack has, but it must have a 1 symbol, at least. Regardless of what the symbol is, but there must be 1, you just tell me what you're pushing. Right? And you can push a 1, you can push a string, you can push nothing. So if I want to, well, we'll see another example. If I didn't push n, if I push epsilon, right? Push epsilon means I'm not pushing anything. Then I could just say A colon, meaning I read the A, I consume the A, regardless of what's on the stack, as long as there is something, and I don't do it, I don't do anything to the stack. Okay? So hopefully it's clear what simplification you can do. But if you're not sure whether the simplification you're thinking about is fine, is understandable, then just write it explicitly. Just write the pop of 1 symbol and the push of the string. Because there is no ambiguity. There is no ambiguity if you do what I just said as well, because we understand each other, right? But if you're unsure, it's probably fine to write it this way. It takes a little more typing, that's it. Any questions so far before I do another example? Okay, let me do another example. The language is W2WR, where W is made of 0 and 1s. So in English is the language of palindromes made so that they are odd length. In the middle there is a 2, and then the left and the right portion are made just of 0 and 1s, and the whole thing is a palindrome, right? Okay, so the 2 here will help us, we'll see, right? Because it's fairly easy to come up with this MPDA. So I do init 0, and I start with some state S. So what do I need to do? Essentially, I need to read the W. I need to remember the W in the stack, right? And so I can say, well, if I'm in state S and I see a 0, I push it on the stack, push 0, which means regardless of what I have on the stack, put a 0 on top of it. But if I have a 1, if I in input, I will push a 1. So whatever the W in input, the first part, right, is, it will just be pushed on the stack so that the last symbol of W is at the top of the stack, right? But then if I see a 2, I go to some state, F, and now essentially the 2 has told me, instead of pushing the symbols on the stack, now I need to match the stack with the input symbol in reverse order, of course, because it is a stack. And so that's very simple. If I have a 0 in input, I must have a 0 on top of the stack for it to be a palindrome. So I must be able to pop a 0. If I have a 1, I must be able to pop a 1. If after having done this, I have Z on top of the stack, Z is really the bottom, right? Then I just say, without reading anything, pop the Z and go to the final state, which is called G. Okay. All right. So as I said, it's fairly easy to see that these assess the correct string, right? If I see 0, 1, 1, I will have on the stack 0, 1, 1. I see a 2, so now I go in popping mode. I'm here, and if I see 0, 1, 1, 2, I want to see 1, 1, 0. And so I have 1. If I have 1 in input, I pop it. I have another 1 on top of the stack. If I have 1 on input, I pop it. And if I have a 0, I pop it. And now I should have just the Z at the bottom. And I read the whole thing, so I just go here and I set. So it's very easy in this case to see that the correct strings are accepted. You must make sure, you must convince yourself that you don't accept additional strings, which unfortunately it can happen because of determinism, etc. So you need to be sure that this is correct. It is. So these assets the palindrome that have a 2 in the middle and everything else is just 0 and 1s. So the interesting thing is, what if I didn't have the 2? What if I just had WWR, W in 0, 1 star? Well, fortunately, we have no determinism here. So all I have to say here is do an epsilon transition, right? An epsilon like this, or just like the 2 means, leave the stack alone. Just do this move without touching the stack, regardless of what the stack contains, as long as it contains something. But of course, if I am here, it contains something because I have Z. Okay? So this one, just changing the 2 into an epsilon, will accept this language, which in a sense is harder if you think about it, because here the 2 tells me when I need to change mode from reading W to reading WR. Here I don't. Well, but this is where I would have no determinism, right? Because this language, actually, we'll see, can be accepted in a deterministic way. I don't need to have choice. I don't have choice, right? If I have a 0, 1, 1, I will push 0, 1, 1. When I see the 2, I know I need to start popping, and that's it. And there is no choices. Here, every symbol could be the end, right? And so I need to essentially make an epsilon transition at any point. But again, this is a little hard to convince yourself that you have set the right strings. It's still easy, the same reasoning. But you also must convince yourself that you don't accept additional strings. And this is where the definition of what the strings accepted are is really important. Because for the clones that jump at their own times, these clones will not accept, either because they jump too early and then they have input left, or because they jump too late and then they cannot match the whole thing, right? So they cannot do the pop Z if you cannot match, all right? But you need to convince yourself that this is correct. It's not as trivial as the one with the 2 in the middle that tells you deterministically what you need to do. Now let me just do one very, very fast because it's interesting. So W in AB star such that the number of A's is equal to the number of B's. So this is an interesting example because it has just two states. All the processing happens in state S, and simply it goes to the final state T if you can pop a Z, which includes the initial state currently, right? Epsilon is in this language. And here what happens is, if I see an A, here's the issue. I need to be ready to read A's and B's in any order. So when I see an A, I can either push a big A to remind me that I've seen one more A than B so far. And I can do that regardless of whether I have Z or A. So actually, let's be careful here, right? So I can say if I have a Z, I can push an AZ. If I have an A and I can pop an A, which means I have more A's than B so far, I push an AA. But if I have a B, what do I want to do? Well, what it means if I have a B on top of the star is that I've seen more B's than A's. So I just want to match this A I just read with the B. So I do just pop the B. And for the B's, I do the similar thing, right? So B, if I have Z, then I push BZ. If I have a big B, I push BZ. But if I can pop an A, I will just do that because I had more A's than B's, and now I match this B with the A. So please look at these free NPDAs on the notes and really understand them, because if you understand these three, you understand enough about NPDA to do homework and to understand how to use them, right? The difficulty in my mind about learning NPDAs is not the definition, it's fairly straightforward, but it is how to make them work correctly. Right, are there any questions? All right, I see people are leaving the lecture, so have a good day. I'll see you on Wednesday.